This is Physics for Lab, where we're exploring magnetic field of a bar magnet, and the main purpose of this experiment was to investigate how the magnitude of the magnetic field produced by a cylindrical magnet varies with distance, and to compare measurements to theoretical predictions. We approached this both experimentally and virtually, physically measured the magnetic field using a smartphone, and carefully accounting for the Earth's magnetic field. In my case, I'm in METS, so I accounted for METS magnetic field. And virtually, we modeled a bar magnet as a magnetic dipole in GlowScript, allowing us to simulate the field in 3 dimensions and compare it with our experimental data. As a preview of the results, we found that the on-axis magnetic field decreases roughly as the distance to the -2 power, and we were able to calculate the magnetic moment of our magnet to be approximately 2.3. The key physics concepts in this lab is that a bar magnet behaves like a magnetic dipole, and for points along the axis of the magnet, the magnitude of the magnetic field is proportional to the magnetic moment divided by the cube of the distance, following the equation for a dipole field. For points off axis, the magnetic field is described by the vector equation shown here, which accounts for both the magnitude and direction of the magnetic moment relative to the observation point. In addition, we used a simplified empirical model of the form magnetic field equals k times r to the n, where n is negative and represents the distance dependence, and this allowed us to analyze our measurements using logarithmic plots to determine both the slope and the constant k. In this experiment, we assumed that the only significant magnetic fields present were from the bar magnet and the Earth, and we assumed that any z component variations were negligible, and additionally we treated the bar magnet as an ideal dipole for data analysis, even though it has finite length, and ignored minor interference from nearby electronic devices or metal objects. For the experiment, the system consisted of the smartphone magnetometer as the observation device, with the magnet and the Earth forming the surroundings, and the initial conditions were set by aligning the phone with true north, bringing the x component of the magnetometer as close to 0 as possible, and the 4 centimeter long and 2 centimeter diameter magnet that I used was placed along the east-west axis on a meter stick. And for measurements, we positioned the magnetometer sensor at specific distances from the magnet, and at each distance, 3 readings were recorded and averaged to reduce experimental noise. And for on-axis measurements, the x component of the magnetic field was recorded, while for off-axis measurements at a 45-degree angle, both the x and y components were used to calculate the net field magnitude. And for example, at 0.10 meters, the averaged x component of the magnetic field was approximately 2.2 times 10 to the -3 Teslas. And as we moved further, the magnitude decreased, so this demonstrated the expected distance dependence of the dipole field. And to extract this distance dependence, we plotted the natural logarithm of the magnetic field versus the natural logarithm of the distance, and this produced a straight line with a slope of approximately -2, confirming the theoretical dipole scaling. And using the intercept of this plot, we calculated the constant k, which allowed us to determine the magnetic moment of our magnet as roughly as 2.3 amperes times meter squared. And these calculations were consistent across multiple distances, providing confidence in both our measurements and analysis method. For the coding part of the experiment in GlowScript, we represented the magnet as a cylinder with its axis along the magnetic moment, and the dipole B function calculates the magnetic field at any observation point using the vector dipole formula. We visualized the field using arrows at on-axis perpendicular and 45-degree off-axis locations, scaling them appropriately for clarity. And the main physics happens in the dipole B function, where the magnitude and direction of the field are computed based on the magnet's moment and the relative position vector, which allowed us to directly compare experimental and simulated values. By the end, both the experimental and virtual models agreed closely with theoretical predictions. On-axis measurements decreased approximately as r to the -2, while off-axis measurements at 45 degrees matched the vector dipole calculation, and the calculated magnetic moment aligned with the expected value for a magnet that of our size, confirming the validity of our approach. Some possible sources of error include slight misalignments of the magnetometer and minor interference from nearby metal objects or electronics, and the approximation of the finite length magnet as a point dipole. To answer the first discussion question of the experiment where misaligned, the x component of the measured field would include a contribution from the Earth's magnetic field, and this would bias our measurements, making the x component values either higher or lower depending on the angle, and the slope could deviate from the -2 that we got, and it would be harder to isolate the bar's magnetic true dipole behavior. So basically we could still do it, but it would be harder. And now for the second question, the magnetic field at each observation point would roughly double, since the magnetic field moments add along the same axis, and the x component values would increase, and the 45-degree off-axis measurements would scale similarly, and the slope of the graph would remain the same because the distance dependence still follows the dipole law. Only the magnitude and the calculated magnetic moment would increase. So in conclusion, this experiment demonstrated that a bar magnet field behaves as a magnetic dipole. Here in METS, using a 4 centimeter farad magnet, we found that on-axis field decreases roughly as r to the negative 2, and the off-axis field at 45 degrees also agreed with predictions. The magnetic moment was determined to be approximately 2.3 amps per meter squared. And that's all. Thank you.